Alright, so we're going to be on page 63 today. On Friday, we started this section together kind of talking about domain and range. And on Friday, I think it was a pretty easy, straightforward day for us because we were just looking at graphing. Okay, graphs in terms of domain and range, tracing our pencil left and right, up and down. Remember doing that? We thought it was okay? Alright, we're going to dive into probably something new for all of us because I'm pretty sure you've never analyzed domain and range before just based off of an equation. So let's say you don't have a graph, okay, you don't have that picture to drag your pencil across. How can you still figure out which x values you can plug in? Okay, which ones work, meaning you'd get out a y value. So we're going to analyze that today. If we weren't given a graph, we just had an equation, how could we still figure out the domain and range? Now what we're going to do is we're going to reference that table at the bottom of page 62. Remember doing that on Friday? So you may have to flip back and forth, or maybe you can look at both pages at once. We're going to kind of use this to our advantage to take a look at some ideas that we can use, okay, or make some connections. So if we take a look, if you want to fill in page 62 at the top up there, let's take a look at the rational function first, okay, which was this first row going across on page 62. What conclusion do you think you can make? We said, I know this is maybe not the wording that we used, but we said on Friday that -2 was not a part of the domain, but -1 was. Okay, we're referencing those x values over here. Why do you think -2 was not a part of the domain, but -1 was? What did we say is our reasoning from Friday? What does it mean to be a part of the domain? Good, Maddie? Has an output, an outcome, yep, a y value. Okay, so in terms of the definition of domain and range, you always need to get a number out as your answer. If you plug in an x, you get out a number for y. If you plug in a y, you get out a number for x. So the fact that we got a number out means that this x value is a part of the domain. Now, we said that this one was undefined, but why were we able to use that word? Why was this outcome considered undefined? Yeah. You cannot divide by 0. We know that, right, in terms of a fraction. And we're going to use that idea today to help us analyze these rational functions. Rational means fraction. So if you take a look on page 63, okay, the first 3 examples, notice how they're all fractions. So what we're going to figure out is what numbers, good morning, anything for the office today? Yeah, we got something over there. Thank you. All right, let's go ahead and write that down. We said the denominator cannot be 0. Okay, you can't divide by 0. So if we can figure out what number or numbers make the denominator 0, okay, the bottom of a fraction 0, then we know those are not a part of the domain. Okay, every single other number is. It's just the ones that make the denominator 0 are not. So we are going to pay close attention to the denominators of these fractions. We don't really care about the tops just yet. Okay, we'll get to that a little bit later in this unit, but right now we're just going to focus on the denominators. So we'll go ahead and say formally the domain of a rational function is all real numbers. Okay, you can pick any number you want. Do we remember the symbol for that phrase? All real numbers? Yeah? The 2 stems, yep. Okay, so the domain of a rational function is all real numbers except, okay, we have some exceptions. Except the values that make, we'll say, the bottom equal to 0. So whenever you're given a fraction equation, you can plug in any single number you want except the number or numbers that make the bottom 0, because we know that that would make the fraction undefined, meaning we don't get out a y value, therefore the x value is not a part of the range or the domain. Okay? So let's just go ahead and take a look at number 1. Can we think about if we were to set the bottom equal to 0, what x value or values we would not have a part of the domain? What do you think, Rebecca?
3 or 1.
3 or 1. Okay, so the 3 is coming from the first factor. If you were to plug in 3, that would make the first factor 0, and the 1 is coming from the second factor. So in terms of our domain, okay, we need to somehow show or represent or write that we can be all real numbers, any single number we want, except 3 and 1. Now, whenever we're talking about all real numbers, we should be able to go from negative infinity to positive infinity. Okay, every single number you want to be. But we need to skip over 1 and 3 because those are the ones that would make the bottom 0. So in terms of our intervals, how do you think we can fill in the 1 and the 3? Maybe with some u's in there because we're skipping over some values. What do you think, Marie? Well, this is positive 3. Sorry. 1 will come before 3. Okay, so from negative infinity to 1, parenthesis, because we're skipping over that 1, we cannot include it. And then a union. And then from 1 to 3, we're going to skip over 3 though, so we have another union. And we're going to go from 3 to infinity. So if you were to think kind of about a number line, okay, you can go all the way to the left and all the way to the right, okay, kind of like your x-axis, but we're going to skip over 1, and we're going to skip over 3. Okay, you can think about those as maybe open circles, maybe an asymptotes on the graph, something like that. Okay, so we can go all the way to the left and all the way to the right, but we're skipping over 1 and we're skipping over 3. So if you take a look at that, notice how we essentially have 3 intervals. We have this left interval, the middle interval, and then the right one. So we need 3 intervals in terms of our notation. We doing okay? Okay, if we have a fraction equation, we got to figure out what makes the bottom 0, because those are the no-no numbers. We got to skip over those. Take a look at the next one. How can we figure out when does x squared equal 9 equal 0? Or x squared minus 9 equals 0? What do you feel like doing? Yeah. Okay, let's go ahead and add the 9 over. And then to get rid of the squared. Yeah. Take the square root of both sides. Now, whenever you square root both sides, we need that plus or minus, because there's technically 2 values that would work. You could do either 3 squared or negative 3 squared, and you'd still get 9. So these are 2 values again that would make the bottom 0. We want to skip over those values. So our domain, we're going to go from negative infinity to positive infinity, but we got to show how we skip over negative 3 and positive 3. So in terms of your number line, negative 3 would come first, and then 3 would come second. Did anyone kind of see a different way to help you solve that one? You could definitely add the 9 and square root like we did. But did anyone notice something else? Yeah. You could factor it. You could have done x plus 3 and x minus 3. Okay, and if that equaled 0, wouldn't negative 3 come from the first factor and positive 3 come from the second? We would get the same values. Okay, so factoring might be a technique we can use. And speaking of factoring, we're probably going to do that for our third one. Okay, so let's go ahead and figure out for our third rational function what makes the bottom 0. How are we going to tackle this one in terms of factoring? If we think about our different techniques, different methods. Is there a GCF we can pull out? No. Does it fit the I am? No, not really. Difference of squares like the second one? No. So our fourth one, yeah. Alright, so a times c, we have 2 times negative 3, which would be negative 6. Add to b, which would be negative 5. Can we think of those two numbers? Multiply negative 6, add to negative 5. Yeah. Negative 6 and positive 1. Okay, so with this technique where we have to do the a times c, we discussed either the grouping process, which I think you guys were more familiar with, but then I showed you the divide and slide. Not sure if we still remember that or like it. Which one do we want to use for this one? Do we still have a preference? Yeah? You like the divide and slide. Okay, so with that negative 6 and 1, we're going to have x minus 6, x plus 1. So we have to divide. Do we remember what we divide by? Yeah.
We divide by 2.
2. Yep, that a value. So let's divide by 2. Let's see, 6 divided by 2 is 3, but 1/2 does not simplify, so this is where the slide part comes from. We could slide that 2 in front of the x as a coefficient. So let's go ahead and figure out our x values. What x value would make the first factor 0? Looks like it's 3 if you plug that in. And which x value would make the second factor 0? Yeah. Negative 1/2. Okay, so our domain is all real numbers, any number you want except negative 1/2 and 3. So we're going to go from negative infinity to positive infinity, skipping over the negative 1/2, and then skipping over the 3. Are we doing okay with rational functions? Does that make sense why we're focusing on the denominator? Okay, we can't divide by 0, so we have to figure out what those exceptions are. Alright, let's go ahead and tackle a square root. Okay, we're still going to look on page 62, so let's reference that for a second. So from Friday, when we looked at the square root function, we said that negative 4 was a part of the domain because we got a y value, but 9 was not, because again it was undefined. So why were we able to use that undefined word in this case? Yeah. You had to use an imaginary number. Okay, so we used undefined previously because we know we can't divide by 0. That's just rational functions. But now that we're dealing with square roots, we know we can't take the square root of a negative number. So again, we're going to have to figure out those exceptions. Okay, so let's say, for instance, do we know what the inside of a square root's called? I'm going to throw in a vocab word. Not sure that you've heard of it before. Do you know what the inside of a square root's called? Maybe not. It's called a radicand. So we know that the radicand aka the inside of a square root, cannot be negative. Okay, we cannot take the square root of a negative number, aka we would get an imaginary number, not real. So if the radicand cannot be negative, that means the domain of a square root function are all the values that make the radicand what? If you can't be negative, then you must be what? Yeah. Positive or what? Or equal to 0. Okay, so if you can't be negative, you're either positive or equal to 0. So in terms of a mathematical notation, how can we show that idea? If you have to be positive or equal to 0, yeah.
A 0 and then you can have less than equal.
Okay, so greater than or equal to 0. So if the radicand, aka the inside of a square root, cannot be negative, then the domain are all the x values that make the radicand positive or 0. So we're going to use that mathematical inequality to show that idea. So kind of very similar to how with the rationals we just focused on the bottom. Okay, in square roots we're just going to focus on the inside. I don't care if there's anything else going on, we're just going to look at the inside. So take a look at our first one. I don't really care if there was a 5 out front. I don't really care if there was a -1 on the end. All I care about is the inside of that square root, because that's where an issue might be. So let's go ahead and take the inside of that square root, x plus 3, and that has to be positive or 0. So we're going to use that inequality to show that idea. Just the inside. Can we solve for x? Kind of simple in this one. We can subtract the 3 over. So this is telling you you can pick any x value you want as long as it's greater than or equal to -3. This is not necessarily an all real numbers case this time. Okay, now we're just looking at certain ones that work. Yes? Perfect. Okay, so what we're going to do is we're going to take this inequality and we're going to translate it or turn it into that interval notation we've been using with brackets and parentheses. If you can equal -3, we need a bracket there. But if you want to be greater than that, you're going to be going off towards positive infinity, which you'll never reach, so you'll need that parenthesis. Okay, so for square root functions, we're just focusing on the inside and trying to figure out which numbers make the inside positive or 0. Okay, let's go ahead and try the next one. Again, I don't care if there was a 7 out front or a +5 on the outside. We're just looking at the inside of that square root. We want it to be positive or 0. All right, so let's solve for x. We can subtract over the 4. And what's going to happen if we divide over that -2? Yeah, you got to flip the sign. Good. All right, so that's our inequality. We can pick any x value we want to plug in as long as it's less than or equal to 2. So in terms of our intervals, okay, brackets or parentheses, what might our domain look like? You can pick anything you want as long as it's less than or equal to 2. Yeah? Negative infinity to 2, and 2 would have a bracket because we could equal 2. We have that bar. Do you guys think you can try the last one on your own? Again, I don't care if there's a -2 out front and we're subtracting 9 on the end. We're just looking at that inside. Any takers for the domain? What might the interval look like? Yeah. Perfect. How'd you guys do? Good? All right, notice no graph, okay, but we're still able to figure out which numbers we should be able to plug in. Okay, all we're doing is analyzing kind of the exceptions of these functions. For rational functions, you cannot divide by 0, so we're going to focus on that idea. For square roots, we know we can't have a negative on the inside, so we're going to focus on that idea. Okay, we're looking at the exceptions. Let's take a look at the back. We have this cube root. Okay, let's take a look at page 62 from Friday, the last one we did, the one at the bottom. We said that negative 11 was a part of the domain because we got a y value out, and so was 5. Do we have any exceptions for cube roots? Do we have any undefined values pop up? Not really, right? And if you take a look at the top of that page, didn't we say the domain of a cubed root is all real numbers? Okay, so maybe we don't really have any exceptions for cube root graphs, but if you take a look on page 64 of our 3 examples here, can you think of which one of those 3 might be a little tricky? Yeah. Why?
Because it has the denominator inside of the bracket.
Exactly. Oh, good vocab. We have a denominator inside of the radicand. Good. Okay, so typically a cube root doesn't have any exceptions. We can put in any number we want for x and we'll get out a number for y. But take a look at how this one is kind of a blend of a rational function because we have a fraction and a cube root. So since it's a blend, we have to make sure we take into account the fact that we have that fraction. So we're going to say typically a cubed root has a domain of all real numbers. Okay. But it depends what's on the inside of that cubed root. But if there is a rational function inside the radicand, what did we have to analyze about a rational function to figure out its domain? What did we have to focus on for a fraction? Yeah.
Must be greater than or equal to 0.
That was a square root.
Oh, sorry.
It's okay.
It can't be equal to 0, sorry.
What do you mean by it?
The denominator.
The denominator. Okay, but if there is a rational function inside the radicand, the denominator cannot equal 0. All right, that greater than or equal to 0 bit was just for square roots. Okay, this is a cubed root, something different. So take a look at our first example here. Do we have a rational function inside that radicand? No. So what's the domain going to be? Yeah. Negative infinity to positive infinity, or you can use that double-stemmed R. All real numbers. What about the second one? Do you have any blending going on? Is it a cubed root and something else, or is it just simply a cubed root? Do we have a fraction on the inside to be concerned with? Not for number 2, nope. So this is going to be another all real numbers. You can put any number in that you want and you'll get out a y value. Okay, so typically a cubed root is all real numbers. But let's take a look at number 3. Okay, so this one should be all real numbers, but we have that exception that we have to analyze. We have to figure out what makes the bottom 0. So can we figure out the exception in this case? which number do we have to kind of skip over? Which number can we not plug in? Yeah. -1/2. So if the domain is typically all real numbers, we can go from -infinity to +infinity, and we got to show how we skip over the -1/2. So we're going to use some parentheses. Does that make sense? Okay, you got to be careful with those cubed roots. There might be a tricky fraction in there. Are we doing okay? I feel like we went lightning fast. No? Pretty good? All right. To be honest, guys, that went a lot faster than I thought it would. Do we want to start the next section, or do you want to try some homework problems? Homework problems? How did I know you guys were going to pick that one? Okay, we'll stop there for today. Go ahead and try some homework problems on page 65 and 66. Okay, we'll start the next section on page 67 tomorrow.